Welcome to Electrodynamics. We're going to do some physics stuff. So we're working through Electrodynamics, Griffiths 4th edition Electrodynamics textbook, and there's this problem right here. And I'm going to work it even though at the end I'm going to cheat. And I'm telling you right now, this is going to be a two-part video. I'm going to do this, and then of course I'm going to do it numerically. And let me just tell you the problem. So we have this sphere with uniform charge density sigma over the surface, and then it's hollow and then inside. And we want to find the electric field at some point z on the z-axis. You can say, well, this is a dumb problem. You can either use Gauss's law or you just know that the electric field's the same as a point charge. But no, we want to do it. Okay, so I'm going to do this in spherical coordinates. And then I'll do it numerically. But we will get to a part where the integral is kind of, and I'm going to graph it. I'm going to do a graphical analysis of the integral in Python. And then we'll do a numerical solution later. Got it. Let's go to work. Okay, so here's my charge distribution, right? So I do have some charge right there. I have my observation location up there. Remember that we have the electric field due to a point charge. dE is 1 over 4 pi epsilon naught dq over the magnitude of r squared r hat. And we can actually write this as, this is the way I like to write it, 1 over 4 pi epsilon naught dq over the magnitude of r cubed times the vector r. And so what that does is r hat is r over the magnitude of r. So I just combine those together. I don't have to find the magnitude that way. But I do need to find r. R is this vector right here. It's from our charge to our location. So let's write a vector for our observation location. Let's write a vector for our charge location. Now, here we have an issue. We could do this in spherical coordinates, but I like to use pseudo-spherical coordinates. So in pseudo-spherical coordinates, I'm going to use the variable r, theta, and phi, but I'm going to write it in terms of x component, y component, z component. That might seem weird, but that's what I'm going to do because I have this on the z-axis. Okay. So just a quick refresher, if I have this as, let's say this would be y, and that's x, and then this is z, and then I have some charge up here. This is, or location, this is the coordinate r, not the vector. This is the angle theta, and then if we project that down to here, this is the angle phi. So x is going to be, we're going to project that down, so it's going to be r sine theta, cosine phi. Y is r sine theta. We project down, and then we do, that's a theta, sine of phi. And then z, we just project over here, and we get r cosine theta. Okay. So with that, I'm going to say my observation location, RO, is going to be the vector 0, 0, z. I'm going to leave it like that, right? Because z is a variable that, it's a parameter, it's not a variable. So, and I want the answer in terms of z, so I'm just going to leave it like that. However, my charge location, RQ, in this case, notice that I'm constrained to the surface of the sphere. So in that case, R is the constant r. So I can put constant r's in there. So the vector RQ is going to be, oh, what? I wrote that twice, is equal to r sine theta cosine phi, r sine theta sine phi, and then r cosine theta. So I have my observation location, I have my charge location. The difference between those two is going to be the vector r. And it does depend on theta and phi, right? We know that. Okay. So the vector r is going to be this minus this. So I get negative r sine theta cosine phi, because it's 0 minus that, 0 minus this, negative r sine theta sine phi. And then for z, I have z minus that. So I have z minus r cosine theta. So that's my r value. Now, what else do we need? We're going to need the magnitude of r. The magnitude of r. So the magnitude of r, I'm going to write it right here, because it's going to get messy. The magnitude of r is going to be this squared plus this squared plus this squared square rooted. So I'm going to say the square root. I'll finish that in later. I get r squared sine squared theta cosine squared phi plus r squared sine squared theta sine squared phi plus, okay, so now I have two terms over here. So I'm going to get plus z squared plus r squared cosine squared theta, and then I'm going to have twice the cross term, so minus 2z r cosine theta, and all of that square rooted. And you're like, wait, whoa, this problem's too hard, we should stop. But we're going to make it a little bit easier, although it will get too hard at the end. But let's just proceed. So we can simplify this sum, right? Because right here, I have sine squared, r squared. So I can factor that out as, I'm going to rewrite these two terms as r squared sine squared theta times cosine squared phi plus sine squared phi. And that is equal to, say it, what? Yes, it's 1. Okay, so that's 1. Now I can take this term and that term, these two terms, and I can factor out the r squared, and I get sine squared theta plus cosine squared theta, and that's 1. Okay, so now we can write our r magnitude as the square root. I have this r squared, and then I have z squared minus 2z r cosine theta. Okay. So these two things we need. So I can plug these two things into this equation up here to get my electric field. Now I do have one more little job to do. I'm going to start erasing some stuff, just so I have that. I need dq, right? I need dq in terms of d theta and d phi. So if I have a surface, let's just draw it as a surface in a sphere of radius r, then what is dA? Well, I like to write dA as dl theta dl phi. That's the length in the theta direction, the length in the phi direction. So in the theta direction, dl theta is just going to be r d theta, right? Because it's the arc length of that circle right there. Now, dl phi is the arc length of the projection down into this xy plane. So this is going to be actually r sine theta d phi. So that means my area element, dA, is going to be r squared sine theta d phi. And that matters because sigma is dq over dA. So dq is going to be sigma r squared sine theta d phi. Whew, that's a lot of stuff there, right? Okay, let's put that up here before I forget it. So dq sigma r squared sine theta d phi. Now we can put it all together and write our electric field. Now, we need to do this. So remember, I have r. So I'm actually going to break this into, let's just put these things over here. Let's put them out of the way. We've got to clean up and put them out of the way. So I have dq. I'm going to put that right here. Can you see that? Yep. dq. I know I'm rewriting it multiple times. Sigma r squared sine theta d phi. R is negative r sine theta cosine phi, negative r sine theta sine phi, and then I have z minus r cosine theta. And then we have the magnitude of r is the square root of r squared plus z squared minus 2r z cosine theta. Okay. So those are all the things I need. Let's just go ahead and erase this, and let's just do the x component. Okay, so the x component, I'm going to have this whole thing right here, and then I'm going to multiply it by the x component of r, because this whole thing's a scalar. So I'm going to multiply it by the x component of r right there. And so we can write that as an integral. So I want to do that. I'm making sure, yeah, I can erase all this stuff. Are we having fun? Okay. Looking at the time. So Ex is going to be 1 over 4 pi epsilon naught dq, but dq is that, sigma r squared sine theta d theta d phi. And then I'm going to divide by this cubed. So I'm going to write that as r squared plus z squared minus 2rz cosine theta to the 3/2, right? Because it's square rooted cubed right there. And then I need to multiply that by the x component of this, which is this. So I have a negative. I'm going to put the negative over here. R. I'm going to put this as r cubed. And then let's just, and sine, so I get sine squared, and then I get cosine phi. And I need to integrate that. I need to do a double integral from theta is 0 to pi, and from phi is 0 to 2 pi, right? Because our theta angle goes from z to negative z, so that's just pi degrees, but phi goes all the way around the circle. Okay, so you may be looking at this saying, boom, I don't want to integrate that. But we can, if we integrate smartly, we can do it, okay? Because looking right here in the phi variable, I can integrate over phi first. I have phi, d phi, and cosine phi. There's no other phi's, right? So I can just kind of just do the phi integral, and all that other stuff is like a constant. I don't have to worry about that. And so I can integrate, if you just integrate, let's put this as 0, phi is 0 to 2 pi of stuff times cosine phi d phi. If you had to do that, what would you get? Well, I can integrate that, and that's going to be equal to, stuff is still an integral. This is stuff. And then I get sine of phi from 0 to 2 pi. But sine of 2 pi and sine of 0 are the same. So when I do the limits of integration, I get stuff times 0. And stuff times 0 is 0. So now I'm integrating from theta is 0 to pi of 0 d phi. And that is 0. So this is 0. You like that? Okay. You knew the electric field was in the x direction was 0 anyway. Don't be surprised. You knew that, right? Because of symmetry reasons. And you could say, oh, symmetry, it's 0. But here you can see why it's 0. Now, if we go back and do EY, we're going to get the same kind of thing, right? We're going to get stuff. And then instead of cosine phi, I'm going to get sine phi d phi. But everything else is the same, right? Because the only difference between this and this is cosine phi and sine phi. So when I integrate that, I get negative cosine phi. But again, I'm evaluating from 0 to 2 pi, so I get 0. Again, you knew that. Don't act surprised. Okay. So there we go. The electric field 0 in the x and y directions. What about z? Okay, now we got to do z. It's not 0 in the z direction. So we got some serious work to do. Let's write it out. Ez is going to be equal to double integral. Theta is 0 to pi. Phi is 0 to 2 pi. And then I have 1 over 4 pi epsilon naught dq, which is going to be sigma r squared sine theta d theta d phi. And then I have r the z component of r, which is z minus r cosine theta. And then I'm going to divide that by the same thing as before. R squared plus z squared minus 2rz cosine theta to the 3 halves. Not a simple integral. But we can get part of it done. I can do part of this because right here, the d phi term, right? d phi, I'm looking no phi, 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 no phi. So it's just stuff times d phi. So I can write this as, let's just put this, the integral from phi is 0 to 2 pi of stuff. Again, I'm going to use that stuff thing. Stuff d phi is going to be stuff times phi from 0 to 2 pi, which is 2 pi times stuff. So that integral right here is just going to give me a 2 pi. So let's just delete that. In the magic, I don't have to rewrite the whole thing. And I'm going to put a 2 pi up here. And then I'm going to get rid of my phi because I integrated already. Now we have an integral that only depends on theta. Remember, z is not a variable, it's a parameter, right? It's just some value. Okay, now we already know something. We know that the electric field is 0 on the inside of a uniform sphere, and it's not 0 outside. So I'm actually going to do 2 integrals. I'm going to do this for z greater than r. And I'm going to do it numerically. But I actually want to plot this function just so we can see what it looks like and kind of get a visual that indeed the electric field is going to be non-zero outside the sphere and 0 inside the sphere. So, but I have this function right here. I'll just call this f as a function of, let's say, z and theta, right? And z, because I want to be able to change the parameter right there. But everything else is a constant. And then I need to pick values. So I'm going to pick, let's pick 1 over 4 pi epsilon naught is just 1. So I'm going to say 1 over 4 pi epsilon naught is equal to 1. And let's say r is equal to 1, but we'll put that in there anyway. So I want to plot this function. I want to plot this function so we can see if it's 0 or not 0 from 0 to pi. I'm going to do it in Python. Okay, so we've got some work to do. Okay. But if you can get to that integral, I mean, you've done some great stuff, and you should be happy with that. So we're going to make a graph. So I'm going to say G1 is graph. Let's just say x title is going to be equal to theta. I'm not going to put units in here. Y title is going to be equal to, I'm just going to call it f, right? It's f, that function as a function of theta. Let's give it a width. And this is not, yeah, this is keep going. 400, height, 200. And now I need a function to plot. F1 equals G curve, color equals color dot blue. I like blue. And now I'm going to define my function. So I'm going to say def f. I'm going to give it a temporary z and a temporary theta. And then I'm going to pass that to it, and it's going to return the value right there. So now I just need to look behind me, and I need to write my function. So we can just do this. Let's just do it in 2 steps. ft, I'm going to call it ftt just so I can write it out more easily. So I have, I'm going to put the whole thing. 2 times pi times k. So let's put up here k equals 1, r equals 1. Okay, so I'm going to use those values. 2 times pi times k, that's that whole thing right up there. And oh, I need sigma too. Sig is 1. You know I'm going to use 1. Okay, times sig times r squared times sine of theta. I'm not going to do the d theta. That's not part of my thing. And then I have times zt. Oh, this should be theta t for temporary. Zt minus r times cosine theta t. Okay, that's that top. And then you divide by, so all of that divided by r squared plus zt squared minus 2 times r times zt times cosine theta times cosine theta t, and then all of that to the 3/2 power. Okay, and then now that I have my function, I'm going to return that. Return ftt. Okay, I don't even know if that's going to work, so let's just try. Let's just say print f of 2 and then 0.5. I don't know. As long as it gives us a number, I think I'll feel fine. Okay, so I think it's working. Okay, so now we can go through our theta values. So I'm going to go over here and say theta is equal to 0, d theta is 0.001. I'm just picking a value. I don't even know if that's too small or whatever. And then I'm going to say while theta is less than pi, I want to just plot that value, theta versus, I did say theta, right? Yeah, theta versus f. So f1 dot plot theta, and then f of theta. Oh, and z. I did pass it z. So z. So I need to say z is, let's say 2. And now I need to increase the value of my theta. Theta equals theta plus d theta. Okay, let's just see if we make a graph. There we go. Okay, so you'll notice that this has if you integrate this graph, the area under this graph, this goes from 0 to 0, the area is a positive number, right? It's a positive area. Now, just for fun, let's make a second graph. Let's make a second graph. I'm going to make up here, f2, let's put a label right here. Z equals 2. Oh, no, I'm sorry. Label equals z equals 2. And then I'm going to make a second graph, G curve, color equals color dot red, label, which we don't actually have to do, z equals 1/2. So that's inside the sphere. So down here, let's just do the same thing. I'm going to copy all this, copy. I always do this. I don't know why it does this. Okay. I'm going to paste it. I reset theta. I'm going to set z to 0.5. I'm going to do the same thing, but this is going to be f2, and everything else is fine. Okay, so I should have 2 graphs, 2 lines. There we go. So here's that first one, but you'll notice that this one has some negative stuff right here and then some positive stuff. So if you integrate over 1/2, it could be 0, right? It could cancel. The areas could cancel. Okay, now we're just going to actually find the area. So let's find the area. We're going to use that same function right there. I'm not going to plot it. I'm just going to find it. So let's say EZ. Let's do it for z equals 2. So I reset that. And I'm going to reset my theta. I don't have to reset d theta. Never change it. And I'm going to say EZ is equal to 0. Then what I'm going to do is just break that up into tiny little rectangles, and add the area up to get the total. So while theta is less than pi, calculate, I'm going to write it as DEZ. So that's the differential element. It's just going to be f of z theta times d theta, right? That's the area of my rectangle. And now I'm going to add it to my total. EZ equals EZ plus DEZ. And then we'll print that. And it won't make any sense, but I'm going to do it anyway. Print EZ equals EZ. Uh-oh. I made a mistake. I didn't increase theta. Good thing I caught that. Theta is theta plus d theta. Sometimes it makes things go poorly if you run it forever. I think hopefully it'll let me run it this time. There we go. So I get 3.14159. Now let's just compare that to the electric field due to a point charge. We do have to find the total charge. Okay, so I do need the total charge. I'm going to write that as, so let's find Q. Q is going to be equal to sigma times the area of the sphere, which is 4 times pi times r squared. That's I wrote it as capital Q. So now let's calculate ETZ, the theoretical z component. It's going to be k times q divided by z squared. And let's print that. Print ETZ equals ETZ. Remember, you know that the electric field should look like a point charge. Let's see if that does indeed work. It does indeed work. Great. Okay, now let's move to z is equal to a half. So inside the sphere, we're going to actually integrate that part and see if it actually is negative. So down here, I'm just going to change this to 0.5. We have a radius of 1, so 0.5 is inside the sphere. And then it's going to rerun the whole thing. And I get 2 times 10 to the negative 6, which is basically 0. Okay, so the electric field inside the sphere is 0. Yay. It's kind of, I like this graph because otherwise it's kind of hard to see that the electric field's 0 inside there. But you can see as z gets less than 0, you do get this negative part, and the whole thing adds up, and so there you go. Whew, that was a lot of work, right? That was 26 minutes of some serious calculus stuff. Now, we're going to do the problem again in the next video. In the next video, I'm going to do this numerically. So instead of having a continuous charge distribution, I'm going to have a finite number of charges that I distribute in the sphere. And we can find the electric field outside, and we can find the electric field inside and see if we get the same result. There's another way you could do this. You could break this sphere into a bunch of rings. Maybe I'll do that, maybe I won't, but I'm definitely going to do the numerical thing, and I will talk to you later.